This is a tabular problem. They tell us that a function f is twice differentiable. Remember, all that means is that the second derivative of f exists, which really means the first derivative exists, which also means f exists, and so f is continuous as well. In the table, they give us some values for x and some values of the first derivative. Okay, part A, write an equation of the tangent line. So as soon as we see those words tangent line, you should be thinking I need a point. So I want to know what happens at 1. And they do give us a point. This is the point that they give us at 1. And then I also need the slope at 1. The slope at 1 is given in the table, which is going to be 8. I have a point, I have a slope. I can write the equation of my line. There's the equation of the line. Okay. Part B. It says use a midpoint Riemann sum with two subintervals. So we're going to do two rectangles, equal length, and we're going to approximate this antiderivative. So this is going to be approximately, and we want to use a midpoint. So when I use numbers from my table, for the midpoint, I need a number in the middle, so I have to go from here to here. So the width is going to be the change in x, which is 0.2. The height is going to be the y value, which is going to be the number in the middle here, which is 10. The next rectangle is going to go from here to here, which is 0.2 again. And the y value here we're going to use is, 13. Okay, you can leave your answer like this. If you want to go ahead and actually figure this number out, 2 plus 2.6 gives me 4.6. Okay. Then it says, use the approximation that we figured out for this. So we figured out this value is approximately 4.6 to estimate the value of f of 1.4. So let's think about what f of 1.4 is. Since you don't have an equation, you can't take the antiderivative of the equation, but the antiderivative of f prime is f. We would do f of 1.4 minus f of 1. So this is what you want to start with. And what they're saying is, this value here is this approximation. So this is 4.6. I'm looking for f of 1.4. F of 1, remember, was given here, which is 15. So f of 1.4 is approximately, really, 15 plus 14.6 is 19.6. So we're using this number here and then using this initial condition. Okay, part C wants you to use Euler's method to do another approximation. So in part B, we did an approximation using a tangent line. Now in part C, we're going to do an approximation using Euler's method. So remember, for Euler's method, we're going to go ahead and create our table. Important thing is make sure that you go ahead and label your table. So my first column is going to be my point. And they give me a point to start with at x equals 1. And again, the y value is 15. Then I need f prime of x, or dy dx. At x equals 1, we know f prime of x is 8. So there's my derivative. And then we need to figure out what the change in y is going to be, or dy. dy is the same as really dy dx times dx. So dy dx is 8. Okay, dx is going to be 0.2 because it says we're going from 1 to 1.4. We're going to use 2 steps. So to get there in 2 steps, you have to go up by 0.2. So 0.2. So this gives me 1.6. Now to get to the next point, approximation on this graph, the x coordinate goes up by 1.2 because that's my dx. So my next x value is 1.2. This is your change in y. So the y value goes up by 1.6. So 15 plus 1.6 is 16.6. Then we're going to repeat this process again. So what is the derivative at 1.2 now? Get it from your table. This is 12. Same thing. 12 times 0.2 is going to be 2.4. This increases by 0.2. 16.6 plus 2.4 gives me 19. So this, using Euler's method, our approximation is 19. So very close to what we got for our approximation part B, using the tangent line. Okay, lastly, part D. This is going back to series from chapter 9 now. They want us to write the second degree Taylor polynomial for f about x equals 1. So if you remember how to create these Taylor polynomials, this is the pattern. I want to know what happens at 1. So your first term is f of 1. Then we find the first derivative at 1 times x minus 1. Then we do the second derivative at 1 times x minus 1 squared over 2 factorial. And so the pattern would continue, but this would be your second degree. So now I'm going to plug in all the information. F of 1 is 15. F prime of 1 is 8. F double prime of 1, notice that was the value they gave us here, is 20. X minus 1 squared over 2 factorial. So this would be your second degree polynomial. Then it says use this polynomial to approximate f of 1.4. So the approximation is plugging in 1.4 for x. So if you do that, this is it. I'm just plugging in 1.4 for x here. And again, you can leave your answer like this. If you punch this out on your calculator, you get 19.8. So the idea here is that using a tangent line, you get an approximation. Using Euler's method, you get an approximation. And then the Taylor polynomial is another way